Welcome back to NANDGAME, maybe for the last time because we are at the end with multitasking CPU. I'm a little bit intimidated because I don't know what a lot of this will entail, and it has the bright yellow preview badge on it, which I'm not sure what that means, but it looks like there is a lot to do here, so let's jump in with timer trigger. The processor we previously built can only run a single program at a time, but modern processors are capable of multitasking. In the following section, we will build a processor capable of multitasking. Multitasking is achieved by having the processor cycle between the different processes and executing each for a short while. If the switching happens fast enough, it feels like the programs are executing at the same time. Multitasking requires memory safety and process isolation. That sounds kind of difficult. A single process should not be able to overtake the whole processor and prevent other processes from running, and processes should not be able to read or modify data of code belonging to another process. To make this all work, we need a way of delimiting the area of memory accessible to a single process. A supervisor process which manages the memory and controls the switching between processes. This is a kernel. We need a timer which regularly interrupts the running process, allowing control to switch to the kernel process, which can then let a different process continue. This event is called context switch. We need a way of saving the state of a running process so it can be restored later. We need a way to give the kernel process rights to memory manipulation, which regular processes don't have. And finally, we need to extend the instruction set with operations to save and restore state and configure memory protection. Okay, that is a lot. Let's start with this one. Timer trigger TR, which is the output right here, should emit 1 every 256 clock cycles. And clock is the signal. So every time this goes 256 times, we should output a 1. And then I suppose restore it back to 0 on the next clock cycle. And then continue that every 256 ticks of the clock. Okay, this doesn't sound too bad. We have a counter here which can count the clock cycles. So that'll just count up every tick. And I guess my first thought here is that we basically set an equalities check. We'll grab, let's say, a bit bundler here. Let's grab an inverter. And if we hook the 8th bit up here, that should be 256. I believe 100 is the hexadecimal value. That's why you see that there, but this should be 256. And essentially any time these equal each other, we want to output a 1. So let's grab a subtract. Okay, it looks like we don't have a subtract, but that's fine. We can invert and then increment by 1 to turn this value over here negative. And I'm just using this inverter here because an inverter not hooked up to anything always outputs 1, means I can switch this bit on, turning this component to the number 256 in decimal. But now through this inverter and this incrementer, we have turned this value negative, and we can simply add them together. So whatever the counter is, minus 256 over here. Okay, now let's grab a bit splitter here and rearrange things just to kind of neaten them up a bit. And I think we can use this 15th bit as sort of a flag. But because we're using 2's complement and we're subtracting our counter minus 256, if it's a negative value, this 15th bit will be on. So it will only turn to 0 once the counter reaches 256. In fact, I'll change this. Instead of hooking up 256 here, I'll set this to 4 for the moment. And we'll reset our state. And you can see it's 1 right now. When I flick it a few times to turn this value to 4, it turns this 15th bit to 0. So let's hook it back up to 8, so it's 256 again. And then we can simply invert this 15th bit and hook that up to our timer trigger output. Now the only issue we have is we got to reset this counter, because if we keep letting it going, it'll just continue to output 1. Luckily we can store a new counter value using this ST here. Anytime this ST flag is 1, it'll store whatever is coming in through X here. Now we don't have X hooked up to anything, so it's just 0, which is fine because that's what we want to restore it to. And we can use what our output is essentially a flag. Anytime the output of the inverter up here goes to 1, we want to reset our counter back to 0. So I'll hook up our store back to that inverter, kind of pin it around. And let's actually hook this back up to 4 just so we can see whether it works or not. So we'll reset our counter, cycle a clock, 2, 3, 4, and you can see our output flag is 1. And then the next clock cycle, it should be back to 0. 1, 2, 3, 4. And then we can just keep doing that to cycle the clock every 4 ticks. The only question I have is whether we actually want to reset the counter to 1 after the cycle click to reset it. That'll be an easy fix of just hooking up an inverter to this X just to output 1. But let's try this out how we have it and just see if that works. Possibly we have an off by 1 here, like I had mentioned. So let's add an inverter that outputs 1 to this X. Let's try that again, and there we go. All right, interesting level. If we had our subtract built in, if we had another component like our equals 0 flag available here, it would probably be a lot easier. But as is, I don't think this is too bad. All right, let's see what's next. Mode controller. The mode controller contains a 1-bit register. Mode 0 is called the kernel mode. Mode 1 is called the user mode. We have our 3 mode inputs here at the bottom. SW input causes the mode to change. TT is the timer trigger signal. It will cause the mode to change when in user mode, but is ignored in kernel mode. All right, for the outputs, SW is 1 when a mode change happens, and that should be regardless if it was triggered by the SW or TR input. MD is the current mode, and IR is a 16-bit number which indicates the cause of the interrupt. So 01 is a timer and 10 is a swap. Okay, so we are doing a lot here, and it may be best to sort of separate our concerns and kind of deal with one output at a time, even though I think these things are going to end up tying into each other. So let's start with MD, our mode. We have a clock here, so we're going to want these things to change on a clock cycle. So let's grab a data flip-flop. I think that's why this data flip-flop component is here. And we'll hook up clock to clock. And for now, let's just worry about our SW input and say we want to store data when this switch gets flipped. And we'll hook the data flip-flop up. We'll assume it starts in mode 0. And if we turn this SW flag on, we want the mode to change at the next change of the clock cycle. And we want this mode to change to whatever the opposite thing it's getting right now. So right now it's getting a 0. We want to change it to a 1. Let's grab an inverter, kind of move these over and hook up the input of the inverter to the output of the data flip-flop. And then the data going into the flip-flop will be the output of the inverter. So now anytime this switch mode is on, we should see the mode output switching anytime a clock cycle changes. So we don't want the mode to change only when this SW is on. We also want it to change when this TT input is on, but only when it's in user mode. That's mode 1. So let's grab an and the mode has to be user mode. So this will have to be a 1, and the timer trigger input has to be 1 as well. It's a little messy, trying to make it look a little bit nicer. So this and will output 1 only when the timer trigger is on and the output of our DFF is 1. So let's change the output to DFF 1, turn the SW off, turn that on, and our output for our AND is 1. And if our output for AND here is 1, that means we want to also switch the mode. So we'll grab an OR and say we want to switch the mode when SW is on or this logic with the trigger timer is on, and then hook that up to the store. Okay, now for this SW output, that is on whenever a change happens, regardless of how it happened. So we should just be able to hook it up to this OR, because if this OR is outputting 1, then we know a change is happening. So that should cover our SW output. Now we just have to deal with IR, which indicates the cause of the interrupt. Since we need specific binary to do this, let's grab a bit bundler. And it might just be simpler to say if the cause is the SW and not the trigger timer, and again, whether the trigger timer is getting used is coming from this AND right here, then we want to turn this bit on, and then do the opposite. If the cause is the trigger timer and not the SW flag, we want to turn this bit on, and then we can hook this bundler up to the output. So this ensures that if the cause is this SW, it'll be 1 0, and if the cause is TT, it'll be 0 1. And I think if they're both off, then we'll get 0 0. All right, let's try this. There we go. 8 components used, not too bad. And looking at this, I think we can maybe simplify it further. I don't know that we need this logic of SW and not TT. So let's get rid of these actually. And how about we just hook this first bit in directly to SW and the 0th bit directly into this AND, which tells you if the trigger timer is on. And let's see if that works. Yep, that works too. Let's just use 4 components instead of 8. Much, much simpler. So yeah, not too bad as long as you break the problem into these smaller bits. Let's move on. Register with backup. A 16-bit register R, which is paired with a backup register RB. The outputs reflect the current state of the registers. Okay, so right there, we know we need 2 registers. So we'll put 2 on the board, and the output reflects the current state of the registers. So we'll set this first register to be our R register, and the second register to be our RB register. And then we'll hook up the clock. We can see there's a clock here, and the registers require a clock cycle. Maybe we can just pin this out of the way because we're going to need some space here. And then it looks like we have a bunch of information here about what all these flags do. We got ST, SB, SW, MD, and then we got 2 16-bit inputs, X and X naught. So you can read all this information on what these flags are. But luckily we have this nice truth table at the bottom here, and we can just work on this. because it looks like ultimately this problem is just about funneling data into the correct registers. And the only way we have to funnel data here is with these select 16. So we have this S here, which is a switch to control whether D1 or D0 gets funneled through. Now we only have one switch, but we have 4 flags. So the select 16 doesn't fully support what we're doing here by itself. We're going to need multiple select 16s. So let's just look at this R here, ignore RB for now. We're just looking at this R register here, and we're going to need to funnel data in 4 different ways, depending on these flags here. So let's grab 4 select 16s. And we've done it in previous levels where we've sort of cascaded data, and that's what we're going to do here. But another way to think of it is sort of an if-else chain. If you've done any programming, you probably have used if-else chains. It's not the best programming practice, but it'll work really nicely here. So we're going to check the conditions on this first switch. And if these conditions, these flags, are correct, we're going to make sure this switch is turned on and the correct data will funnel through D1. And if not, we'll funnel data through D0, which will be coming from the second select 16. We're going to check conditions here to see if these are correct. And if they are, we're going to funnel the right data to that select 16 through D1. If not, we're going to go through D0 and just do the same thing. Check if these conditions are met for this select 16. If not, we're going to funnel data through this select 16. So if it doesn't make sense, hopefully it does once we start building it out. Again, we're going to ignore RB for now, or just focus on R, this first register here. And we can look at these conditions. When ST is 1, SB is 0, and SW is 0, we want to funnel the X value through. So that'll be the condition for our first select 16. So let's hook up X, because X is the value we want to go into our register here. But we only want to do it if these conditions are met. We have 3 conditions, and previously I had built this custom components as 3 and that was really just for demonstration. I'm trying not to use custom components to solve problems, but this is just a way to get 3 conditions working in a single and. If you go into custom components, you can see it's just 2 ands daisy chained together. So that's what we're actually going to use. Throw away this 3 and get 2 ands, which we will daisy chain just like that. Let's give ourselves a little more room to work with. Now our first condition is ST is 1, so we can hook up our first condition there. And then we have SB0 and SW0. So we're going to invert the SB and SW flags. And it looks like we're going to do that a lot, so I'm just going to hook up inverters to all these flags just so we have them available. So again, for this first one, we want ST and not SB, so we hook up to the inverter, and not SW. So we hook it up to the SW inverter. And then this and, if this and is 1, we want to store D1, so we switch that on. And now, if we have ST1, SB0 and SW0, we don't really care if this MD is on or off, which you can see by this dash here. You can cycle the clock on and off, and you can see nothing happens because we need this store value to be active in order to transfer data into this register. Now we're gonna have to turn store on in various conditions, but for now we can just hook it up to this and, cycle the clock, and there we go. We got our value from X, which is decimal 100, into our output. Now I'm gonna unhook this store up for now because we're gonna need to do something different with that, but we've got our first condition for R working. Move this a little bit just to make it a little more compact. Now this next line does nothing with RR register, so we're going to go on to the 4th line here where we want to funnel RB. So that's our second select 16 here, and this is our RB register, and we want to funnel the output of the RB register into the input of our D1 here. And to turn this selector on, we want ST to be 0, SW to be 1, and MD to be 0. So again, we're going to need 2 ands, daisy chain them together like we did previously to get a triple and. The first condition is not ST, so we can hook that up to the inverter. The second condition is SW, so we hook that right to SW. And the third condition is not MD. Then we can hook this and up to our switch here so that when this is 1, it will funnel the data from our B register here. Moving on, we have our third select 16, and in this case we want to funnel X naught into our R register, so we'll hook up X naught right there, and we want to do it not ST and SW and MD, so we need another triple and here, daisy chain those together, and we'll hook that second and up to the switch so that when these conditions are met, it will trigger D1 coming from X naught here. And what are the conditions? Not ST and SW and MD. So not ST, we'll hook that up to the inverter, and SW, hook that directly up to our SW flag here, and MD, hook it up directly to the MD flag here. So that when these conditions are met, X0 should funnel funnel to our register. Finally, we have this line here where we have 4 conditions that need to be met: ST and not SB and SW and MD. We're going to need a quadruple AND. Pretty simple to make, actually. You just need 3 ANDs instead of 2. And we can just hook these 2 ANDs together like so and hook that up into our switch. So we got AB on the first AND and AB on the second AND. We'll hook up this first one to ST, and the second one is not SB. So we'll hook it up to the inverter, and SW and MD. And it looks like in that case, we also want to funnel X naught. So we have to hook up our D1 to X naught. Now we need to get the store flag working on our first register, otherwise no data will actually go into our register. And when do we want to store data into a register? Again, it's when these conditions are met, these 4 conditions. And we've already set up these AND components with the logic to check whether these conditions are met. So we need to check if this condition is met, or this condition is met, or this condition is met, or this condition is met. So that's 4 conditions. So we need a quadruple OR. We can set it up the same way we set up our quadruple AND. We need 3 ORs. Rearrange it slightly. Hook A into our first OR and B into our second OR. And then we hook up the inputs to the ORs to the same ANDs that are being input to our switches here. So this is the first condition, second condition, third condition, and fourth condition. And then we can hook up the output of this OR to our store switch here. And now this first register is all hooked up and it should just work. We can test it out. So right now it's got 100 in it coming from our X input here. But let's say we want the input from X naught to go in there. Let's put 50 in decimal just to try it out. And what flags do we need? We'll try this one. Store set to 0. It doesn't matter what SB is, SW1 and MD1. We'll cycle the clock. And you can see 50 is our output for our decimal here. So that all works. Now we just need to hook up the RB register. So we'll add more select 16s to funnel data into our RB register. And just like the first one, there's 4 conditions in which we're funneling data to our RB register here. So we'll grab 4 select 16s, and then we will connect them just like we did with the first register by kind of cascading them. So this one will be this condition here because it's our first condition, which we actually have to funnel RB. And in this instance, we're going to be funneling the X data, the data from the X input into it. So we can hook that up to D1. And of course, I forgot we have to hook up our X input from our register to this first select 16. Can't forget to do that. Okay, and then what condition do we want this switch to turn to 1? ST and SB and not SW. So we'll grab another triple AND, daisy chain them together as we've done before, and hook that up to our first switch here. And we want ST and SB and not SW. So let's hook this store up just to test it out. We're going to disconnect this in a minute here, but we just want to test that if we have these conditions, if ST is 1, SB is 1, and SW is 0, and we don't care what MD is, that our value from our X input here will cycle to our RB register. So let's run the clock. Perfect. Our register is still 50, so nothing changed there. That's exactly what we want to see. So then we'll hook the rest up. Let's disconnect this store here. And conveniently, we already set up the logic for these last 3 conditions. So for this condition here, not ST and SW and not MD, we should just be able to hook it up to this same AND. And then same thing for our condition here. We can hook it up to this AND. And again, for our final condition, we can hook it up to this AND right here because we're just repeating the same logic. And now we just have to make sure the right data gets funneled to these selectors. So for our second selector here, we want to funnel the data from the R register. So we'll hook up D1 to the R register. Our third selector, same thing. We want to hook up data from the R register. And our fourth selector, we want to hook up data from our X input. Now, to get this store set up for their RB register, we need to do the same thing with this quadruple OR. Now, luckily, this OR right here, this bottom one, should be the same logic for both registers. So we're going to use this OR as well. So we're only going to need 2 more ORs. We'll hook up this OR into our A, hook up our second OR into B. Because this OR right here covers these last 2 conditions, we just need to deal with these middle 2 conditions, which should be coming from this AND right here. And I believe the second AND right here. Yep, that's going into the selector, so that's correct. And then we need to hook up this OR to our store on our register. And I believe that's everything hooked up and working. Instead of testing it out, let's just check solution and see if we got it right. All right, there we go. 30 components used. It's a lot of NAND gates. Of course, this is a very messy one with all these wires crisscrossing. Maybe I can kind of rearrange the components to make it look a little nicer. Maybe have it look like it makes a little more sense. Maybe that helps. I don't know if it does, but I hope you understand my explanation because I know this just looks very messy. Okay, let's move on. Program counter. So we need a register with backup with 2 additions. If the ST flag is 0, the program counter is incremented and stored in PC. And on interrupt, when SW is 1 and MD is 1, the number 0 is stored in the program counter. So this is pretty light on instructions, but let's grab our register with backup. And I think we can safely hook up some of these things. So we'll hook up the clock. We'll hook up our MD and SW flags. We don't really have an X not, so we're just going to hook up X. And then we can hook up SB to SB. And we have a J input here and an ST. But we do have a PC, which is I think is supposed to go to R, and PCB, which is I believe supposed to go to RB. And let's maybe assume that ST is supposed to be J. I'm not really sure about that, but let's just say we have this hooked up correctly without these current additions they're talking about. So first, if ST is 0, the program counter, which is this register here, is incremented. So we just need to add 1. So we do have an incrementer here, and we're going to need a selector. So we'll hook up selector to our J here. And if J is 0, if ST is 0, we want the output of the register incremented by 1, so we can hook that up to D0. And we'll hook that up to our X input. And then we can say if it's 1, we want to be coming from the X input from the bottom here, is what I assume they want to happen. Now we have another condition we need to deal with, which is if SW and MD are 1. So let's grab an and here, this will show us if SW and MD is 1. Grab another selector, and in that case, we want the number 0 stored in our register. So if that's 1, we just don't have to do anything. Now we can't hook this up to our X directly, but we can daisy chain. So we'll hook up this D1 to our second selector here. We'll check our first condition, whether ST is 0. If it is, we'll do an incremented version. And then it's sort of like we are checking different conditions. If ST is 1, we will grab the previous value and store it into X. If it's not, we'll check this selector. And if that's 1, if these two flags are 1, we will store 0. And if not, we will store X. I think this should work. Let's try it. Oh, of course, it doesn't work because when J is 0, you can see it's not incrementing at all because our store isn't on. So maybe J is in store and we just have to have store always on. Let's grab a NAND and just have that always be on. Let's try it. And you can see now it is incrementing like we expect. Let's check solution. Oh, and there, that works. So this is a little confusing. I think we probably need a little more explanation here would be helpful. But if you read this as if J equals 0, I think this makes a lot more sense. But to be fair, this is a preview level, so maybe a little more work just needs to be done on it. Let's move on. Register bank. Okay, this is a big one with a lot of inputs and outputs. A block of 4 16-bit registers, A, D, M, and PC, each coupled with a backup register. Okay, so let's just start there. We'll grab 3 registers and our program counter, which we just built, and we'll just hook them all up. A and AB goes into the R and RB, and then same thing with the rest of them. Okay, so if A equals 1, store X in A. So A is our store flag, and we want to store X. If D equals 1, store X in D. So D will be our store flag, and we'll store X in D. If M equals 1, store X in M. So again, M will be our store flag, and we're going to store X in there. And if J equals 1, store PC input into the PC register. So J goes to J, and then we want to store our PC input to this PC register. So we'll hook that up to X. If SB is 1, store instead into the corresponding backup registers. I think we just have to hook up SB for each one to the SB on the inputs. That should let that one work. Okay, so mode is the current mode. SW indicates a mode change. When SW is 1 and mode is 1, these values are stored into the following registers. I think this is the same thing. I think we can just hook up SW all the way down the line and then MD all the way down the line. And then we use the X naughts to funnel these values. So AB to A, so we'll hook up X naught to this RB up here. IR input to D, so X naught should go to IR. and the number 0 to M. So in that case, we could just leave this X naught hooked up to nothing because that will funnel 0. Okay, then we have to hook up the clocks. Of course, it won't work without the clocks working. And I'm not fully sure I did everything right, but let's try it. There we go. Compared to the rest of them, a bit of an easier challenge because it's just hooking up these 4 registers. Let's move on. General purpose memory. In the first processor, instruction memory and data memory was completely separate. This makes for a simple design, but means there's no way to install new programs or update existing programs. To enable this, we need memory which can be used for both instruction memory and data memory with read/store access. We start with a memory block of just 4 cells. The same design can easily be scaled up to larger range of addresses. All right, the unit contains 4 16-bit registers accessed with a 2-bit address. All right, so right off the bat, it's pretty clear we're going to need 4 registers. So let's just get those on the board. A0 and A1, that's down here, is the A address, and that will output to the A star output. In other words, if A1 and A0 are 0, 0, we're going to be looking at this register. 0, 1, we're going to be looking at the second register. 1, 0, we're going to be looking at the third register. And 1, 1, we're going to be looking at the fourth register. If this store flag is on, then the X input is going to be stored at whatever the A address is. And the I output is the value stored at the PC address given by PC0 and PC1. And whatever this address is, so if this is 1, 1, we're going to take this fourth register and output that value to this I output. And then CL is just the clock. Easy enough. Let's start just by hooking up the clock. And then we can also hook up X to all the registers. And the reason for that is because if we want the X value to actually save in a register, we're going to have to toggle this store on and off for each one. And we'll do that individually by creating logic around these A1 and A0 flags. So let's actually get some ANDs, and we're going to need an AND for each register. And so that will create what is essentially a single flag, which will determine which register we want addressed. So 0, 0, you want not A and not B. So we're going to need some inverters here. We might as well just hook them up. So you can see if the A address is 0, 0, this AND for our first register will be on. Our second register will be 0, 1, so not A1 and A0. So we hook that directly up to the A0 flag so that if it's 0 and 1, this will flag 1. Our third register will be 1 and 0. So we hook up A directly to A1 and B to the inverted A0, so that if it's 1, 0, this will be on. And then our fourth register will just be 1, 1, so we can just hook those directly up to the flags, so that if it's 1, 1, this AND will be on. So if we want to store a value in these registers, we have to have the proper address set by A, but then this store also needs to be on. So we'll need to grab another AND to deal with that, where A will be the output of our first AND and B will be store. And then we can hook that up to the ST of the register. And we're going to repeat that for all of them, where we hook up another AND to the output of our first AND store, and then hook up that AND to the ST, the store of the register. Repeat that again over here. We'll grab another AND. A will be the output of our first and B will be ST from our input, and we hook that up to ST on the register. And for the fourth one, the same exact thing. We hook up A to our first and B to the store, and hook up this AND to the ST, the store on the register. And with this setup right here, we should be able to funnel whatever values we want into these registers. So if we want to add the hex value, say 50, to our first register, our 0, 0 register, we set this A1 and A0 to 0, 0, and then we just cycle the clock. And there we go, we got hex value 50 into this register. If, say, we want our third register, that would be 1, 0, and we want to store the hex value 25, let's say, cycle the clock on and off, and we get hex value 25 into this third register. All right, so that's the X input of the registers working. Now we have to funnel the correct register to this A star output. And we're going to do what we've done a lot in the past, is we're going to use these select 16s to cascade the correct value. So we've grabbed 3. So we'll hook up our S, our switch, to our AND here. Not the one that's connected to the store flag, because we are going to output this to A star whether or not this ST flag is on or off. We're just hooking up directly to the AND connected to the A addresses. And if that's 1, then we want that coming from our 0, 0 register, which is the first register here. So we hooked up D1 to that first register. And if not, we will cascade from the second select 16, which will be hooked up to this AND from our second register. And again, we hook up D1 to that register, because if it's 0, 1, then we want to output it to D1. If this switch isn't being activated, then we want to hook up D0 to the next, select 16, and we will hook that up to the third logic for our register and hook up D1 to that. And then instead of having another select 16 to deal with it, we can just hook up D0 directly to our fourth register because there's no other options for our flag. This first one deals with our A flags being 0, 0. The second one deals with our A flags being 0, 1. This third flag deals with our flags being 1, 0. And the only other option is 1, 1, which is this fourth register. So that's why we can hook up D0 directly to that fourth register. And then we hook up this select to our A star. So now this should work if we want our, say, third register to output to A star. Our third register is 1, 0. So we set our A address to 1, 0. And you can see our value from our third register is hex value 25, and that is going to the output. So now we have to deal with this I output. And luckily this is pretty simple. This I output is determined by this PC address, and we can just replicate the same logic with our inverters or our ANDs that we did for the A address. Maybe I can push these things a little bit closer together so we just have a little bit more room to work with. So let's grab 2 inverters because we're going to need them just like we did for this A address. Hook them up to PC1 and PC0. And let's grab 4 ANDs here. And these will correspond to our first register, second register, third register, and fourth register, or 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, A and B hook up to the inverter of PC. 0, 1, the first one hooks up to the inverter. The second one hooks up directly to the PC0 flag. Third register, 1, 0. The A hooks up directly to the PC1 and B hooks up to the inverter of PC0. And 1, 1, our fourth register hooks directly up to the PC1 and PC0 flags. So you can see PC is set to 0, 0 right now, and that is showing our first register flagging and the others are 0. If we were to say set it to 1, 1, it'll be our fourth register flagging. So then again, we can just replicate our cascading select logic here. We'll grab 3 selectors. The first one will be a switch on the first AND, the second one will be a switch on the second AND, and the third one will be a switch on the third AND. Again, we cascaded, it's just the same logic, so we can just hook up D0 on the first one into the second one, and on the second one into the third one. And then D1 will be coming from our first register for the first selector. For the second selector, D1 will be going into our second register, and for our third selector, D1 will be coming into the third selector, and D0 will be going into the fourth selector for that same reason. If this is 1, 1, then there's really no other options. And that actually makes this AND obsolete, so we can just go ahead and delete that. And then we're going to hook up this first selector into our I output. So right now, PC is set to the fourth register, which has 0 in it, and you can see 0 is being output. Let's actually put something in this fourth register to test it. To do that, we switch A to 1, 1, store to on, and let's put, I don't know, the number 4 as a hex value, cycle on and off, and you can see there is a problem here. I'm actually using selects instead of select 16, so that's why nothing is working. So let me quickly replace that. Okay, so I've done nothing different but replace the select with a select 16. You need a select 16, obviously, because this is a 16-bit number coming through. And now you can see that this is working. We're getting our hex value 4 from our fourth register coming through to the I output. And that should be everything we need. Let's check solution. And there we go, general purpose memory complete with only 25 components, which I think is pretty good. Next level. Virtual memory. I noticed that there's no actual check implemented in this level, because if I come out here, it looks like virtual memory is already solved, but I haven't done anything. So if you hit check solution, it just tells you that the level is successfully completed. So if you're feeling lazy, you could just move on and not worry about this one. I will attempt to solve it in a way I think makes sense, but obviously we're not going to be able to fully check that it works as intended because we get level successfully completed no matter what we do. But we're going to try. Extend the 16-bit address A and PC by prepending 3 bits from M. Bit 15 of the input address determines which 3-bit block is used. So here we can see if bit 15 of PC is 0, then we want to grab bits 0 through 2 from M and prepend that into the address. If bit 15 on PC is 1, then we want to prepend bits 4 through 6. A, we're going to prepend bits 8 through 10 if bit 15 is 0, and bits 12 through 14 if A is 1. The high bit, that is this 15th bit, are going to be discarded from the input address, from the address from A and PC, and instead the selected 3 bits over here are going to be
be prepended given the 18-bit address. The read-only flag, that will be bit 11 and bit 15 on A, depending whether bit 15 is 0 or 1, determines if data can be stored. When 0, data can be stored normally by using the ST flag. When 1, the ST flag is ignored. Okay, maybe we'll deal with that bit last. I suppose we are going to need a bunch of bit splitters, one for A, one for PC, and one for M. Hook those up. And of course, we're trying to address memory here, and we do have a RAM 18, which is an 18-bit addressable memory. So we've got that thrown up on the board, and I suppose we can just hook up the outputs A star and I, and we can hook up the clock and just sort of get the clock out of our way. And we're also going to need a bit bundler. I only see a 16-bit bundler, but we need to deal with 18 bits, so I'm not sure how we're going to do that. Okay, so it's labeled as 16-bit bundler, but it is actually an 18-bit bundler. So that's just a little error that needs to get fixed. And I suppose we're going to need two of these because we need one for the PC address and one for the A, the address right here. And I can already tell this is going to start to get a bit crowded. Let's try to move some of these down to give ourselves more room. Okay, so this 18-bit bundler will go into AD for the address, and then this second one will go into PC. And I guess the first 15 bits, so 0 through 14 on both of the A and PC here, will be the same no matter what. We're just kind of pre-pending at the end here, so maybe we can just hook those up right away. Because yeah, these bits should not be affected at all. Okay, so maybe we move these up here because I think we're going to need a lot of space to deal with this pre-pending issue. And we can also hook up X directly to X like that. And again, we're going to deal with that store logic of X second. So it would be really nice if we just had a regular selector. We don't, we just have the select 16, which is a bit annoying because since we're just using this 15th flag to determine which bits go into 15, 16, and 17 here, a single 1-bit selector would be really nice to have. So we're going to have to basically rebuild a selector using the components we have here. So here's how you do that. Here's how we did it originally, quite a long time ago now. So we need an OR, 2 ANDs, and an inverter. And then we're going to need that for each output bit here, 15, 16, 17 for each one. Luckily, we do have those components available to us. We're just going to have to sort of cover up the screen to get everything working. So I've just duplicated the single bit switch logic here. I'm not going to cover how that works because I already did, and I will link to that video. But it does look like it's working. If the 15th bit here is 0, then we're grabbing from bit 10, which is 1, and looks like we are outputting 1 here to bit 17. And if this 15th bit is 1, so let's change this. So it's 1, we should be grabbing from the 14th bit into bit 17. And it looks like that's working. So we're just going to duplicate this logic for bit 16 and 15 in A, and then 17, 16, and 15 in PC. Luckily, we can use this inverter again, so we will just need some more ORs and some more ANDs, and then we will need an inverter on our PC as well. So I will just duplicate that logic real quick. All right, so I've just duplicated everything for these other bits. They're all hooked up, and let's see if it works, since we have to test it out ourselves. For our A, if the 15th bit is 1, which I have it set to right now, we should be getting bits 12 through 14 from M, which are all set to 0, and it does look like they're all outputting 0. If we switch it so the 15th bit is 0, then bit 17, 16, and 15 should be getting bits 10 through 8, which is 1, 0, 1, and it looks like we are outputting 1, 0, 1. Perfect, so that A works. Now let's look at PC. Right now I have it set to 0, so it should be getting bits 0 through 2, which is 1, 1, 1, and it looks like it is outputting 1, 1, 1 to bits 17, 16, and 15. And if we switch it to -1, so that our 15th bit flag is on, we should be getting bits 4 through 6, which is 1, 0, 1, and it looks like we are getting 1, 0, 1. So that all works. The pre-pending all works. Now we just have to deal with this store flag, or the read-only flag. So if store is on, that's 1, and bit 15 is on, that we can turn store on RAM. So that's just a single AND, pretty simple. Hook that into store, and then hook that into bit 15, and then hook store to that AND. Or, so actually let's disconnect this because we're going to need an OR here. Let's hook that OR in, and hook that and to the first part of that or if bit 15 is 0 and store is on and bit 11 is on, then we can also turn the store flag on. So we're actually going to need a three-way AND, which just requires two ANDs daisy chained together. So hard to find room for this, but we will say daisy chain our B input into this AND, and then we'll have A in this first AND and then A and B in the second AND to deal with our three conditions. So if bit 15 is 0, so we want to hook up that to our inverted bit 15, and store needs to be on, which is A, and bit 11 is on. Look that up here. Then we can also turn the flag on, so we'll hook up that to that B part of our OR, and that should work. So if store is on and our 15th bit is 1, then it looks like store is being turned on, just as we want it to be. Or if store is off, but bit 11 is on, so 15 is 0, but 11 is 1, and store is on, this number satisfies that condition. 15 is 0, 11 is 1, and store is on, then store should also be on. In other conditions, like if we turn that off, store turns off. All right, so I believe this is all working and all hooked up correctly. I can check solution again, but not gonna tell us much because it will pass no matter what. But I believe this is working exactly how it's intended, exactly how it's laid out in our instructions. And yeah, it would look a lot cleaner if we could use a single bit switch. Maybe that'll get added into the default components. But otherwise, really not too bad. Let's move on. Control unit. Oh, this is a big one. I can't even see the full screen. Here, let's zoom out. Decode the I input into an instruction. The leftmost bits determine the instruction set. All right, so let's grab a bit splitter right away. And bits 15 and 14 determine whether it's a data instruction, an ALU instruction, and then if bit 14 is 0, then we need to decode the rest of the bits like this. And then we have a bunch of flags we have to deal with that will determine which input register we're using. And when SB is 1, the backup register is used instead. All right, so let's just maybe start with getting the data instruction working. So it looks like we get to use the control unit that we built way back over here. So it's worth remembering what that does, which is takes in an instruction and some register states. And if it's an ALU instruction, the R outputs the result of that ALU instruction. If it's a data instruction, it just outputs the I data instruction. And then we have our destination flags, and then we have a jump flag. We'll come back here. Let's put this off to the side for the moment. It looks like this control unit should handle a lot of what we need to do. We can hook up the instruction directly to this control unit and hook up the A, D, and A star registers. A star is right here. We are probably going to have to adjust these because we'll have to potentially use these backup registers instead. And of course, we still need this on the board because we need to deal with all these other bits of the instruction and what they do. But let's just get this part working first. We have these flags, J, A star, D, A, and then I think X can hook up to R. So this by itself, I believe, should be able to handle a data instruction and ALU instruction. But if bit 14 here is 1, then we need to deal with all of these things. So let's move our control unit over here so we have a little more room to work with. And we're going to need to create a flag to see whether we need to deal with these extra steps. So let's grab an AND and an inverter. So it should be 15 and not bit 14. And if the result of this AND is 1, then we're going to need to do some things. So bit 13 is swap. So if this flag's on and bit 13 is on, then we want to turn this swap on. So we'll hook up an AND to bit 13 and our flag here. Bit 12 through 9 are unused. These three bits, 8, 7, and 6, are going to deal with the source register, and that's down here. We'll look at that last. Let's look at the destination register instead. We'll grab another AND. And if bit 5 is on, then we want the A flag to be on. So we need to check this flag right here and bit 5, and that'll turn this A on. So we want this A on in two situations. One, if this triggers 1, or if this A is on and these flags aren't set. So we're going to need to grab an AND and hook that A up into AND. And we want, it has to come from A and not this flag, so the inverse of this flag, or disconnect that, or coming from here. In other words, if we have bit 15 is 0 or bit 15 and 14 are 1, then it will flag on depending on whether its control unit tells it to. If bit 15 is 1 and bit 14 is 0, it will only flag on if this flag and this bit tell it to. We can then repeat that logic for the rest of these. So we'll do D next, we'll grab an and if this flag is on and bit 4 is on, then we want that D flag on. Or if this flag is off and this D is on, then we want that flag on. Grab an OR and another and we want the B hooked up to the inverter, telling us that this is off, and the A hooked up to our D here. And this other OR can come right here. We're going to repeat that logic again for the rest of these. So we'll need 4 more ands over here. All the A's get hooked up to this flag right here, which tells us that bit 15 is on and bit 14 is off. And then all the B's get hooked up to their respective bits from the instruction. And then each of these, plus the J here, are going to need an OR and an AND. We'll hook up the OR to the flags, and then the B from the OR should be coming from these ANDs right here. So A star should be coming from this one, M should be coming from the next one, J should be coming from the one after that. So that's a little bit out of order, it looks like. And then SB, I think, is the same thing as B over here. So that should be coming from the bit 0 and. Now the A from all these ORs should be coming from the respective ANDs below it. And then the B from the ANDs should be coming from this inverter right here, which tells us that this flag is off. And then the A should be coming from the control unit. So A star comes from here, and J, the one that's hooked up to J, should come to J. Oh, and actually there is no output from the control unit for M or SB, so we don't actually need to do this OR here. We can just delete that, and instead they can come directly from this AND. So M from this one and SB from this one, since the control unit has no way of switching these flags on or off. Then we need to deal with these source register flags, which are bits 6, 7, and 8. So as we've done several times in the past, we're going to create a sort of cascading selector. Let's pull this down so we have a little bit more room. So bit 7 is S0, bit 8 is S1. But I think before we do that part, we will deal with SB here. SB selects the backup instead of the main. So if SB is on, we're going to select AB instead of A, DB instead of D, MB instead of M, and PCB instead of PC. So we'll grab a selector for each one of those and hook the switch up to bit 6. And that's going to be for all of them. If bit 6 is on, we want to select the backup for the register. So this first one will hook up D1 to the backup for A, which is AB. The second one will hook up to DB, third one to MB, and fourth one to PCB. And if it's off, if this is 0, then we want to just select the register itself, not the backup. So D0 will go to A on the first one, and the second one, D0 will go to D, third one, D0 will go to M, and the fourth one, D0 will go to PC. So now coming out of these selectors will be either the main register or the backup, depending on whether this SB flag, bit 6 here, is on or off. All right, so now we want to select the right one based on the S1 and S0 flags, that's bit 7 and bit 8. So if bit 7 and bit 8 are both off, then we want to select register A here. So we will grab an AND, move these kind of up to give us more room to work with. And we're going to need a couple inverters, one for bit 7 and one for bit 8. Hook one up to bit 8 and one up to bit 7. And not bit 8 and not bit 7, we want to hook up to this first AND because that will select our A register. So we can hook up D1 into this first selector. If that's not the case, we'll select whatever's coming from D0, which will be the next selector, and that will be register D, and that's not S1 and S0. So we'll grab another AND here. S1 is bit 8, so we want to get the one coming from the inverter from bit 8, and S0 is just directly from bit 7, and we'll hook it up to that selector. And in the case this is a 1, this AND is a 1, we want it to come from the D register, which is our second selector here. If that's not the case, then we'll check again on the next selector coming from the D0 input, and we'll check M. So that'll be S1 and not S0. So we'll grab another AND, hook that into our selector, and hook it directly to bit 8 for S1, and to the inverter to bit 7 for not S0. Okay, oh, and we got to hook up this selector. So D1 will be coming from the M register and D0 will be coming from PC. Because we're coming for all these options, if none of these flags match these 3 options, then it has to match the case where they're both on, in which case it'll funnel through this D0, which will be coming from the PC. So I was a bit confused about where to hook up the output from this select 16. Again, this is the value coming from these registers here. And it looks like I need to hook it up to the X and PC outputs, but I'm assuming only if this flag right here is on. That's where bit 15 is 1 and bit 14 is 0. So we'll need another couple of 16-bit selectors. So there's one for our X output here, and the selector will be again on this flag right here. If it's on, then we want it to be coming from the cascaded selector tree that we have here, and if it's off, we want it to be coming from R from the control unit, and then we can hook that directly into X. And I was going to grab another selector, but I think I can just hook it up right here to this selector to PC. So now they are both outputting 13, just like we have in this test here. Let's see if it passes all the tests. And there we go. Level successfully completed. So the control unit aspect here isn't too bad, at least dealing with these first 2 instruction sets, because we're just using the control unit from the previous CPU we built. It's just hooking up everything else here and funneling data where it needs to go and switching the correct flags when they need to be switched. So yeah, you end up with something that's pretty messy, but I think logically not too complicated. And with that, we move on to our final level processor. We just need to connect all the components we made in order to create a processor with support for multitasking. So let's grab everything: a register, memory, we're gonna need a clock, our mode controller, our trigger, and our control unit. Of course, connecting everything up is going to be easier said than done because there's a lot of inputs and outputs here, and it's a little bit tough to tell where everything goes. But let's just start simple and set up the clocks. So everything, pretty much except for the control unit, requires a clock input. So we will hook all the clocks up just like that. Then the next easiest thing is probably to deal with the output of this trigger. I believe that should go to TT in the mode controller, or trigger timer. And that's the trigger component all done, and the clock component all done. 4 more components to hook up. Let's continue with mode controller, and I believe this SW input on mode controller should come from the control unit SW output. I say that mainly because there is no other SW output to choose from, but I think that should work. And then the outputs for the mode controller should go into the registers. You can see here it lines up perfectly where IR goes into IR, SW goes into SW, and MD goes into MD. And then I believe the rest of these inputs from the register should come from the control unit output. So A goes to A, X goes to X, D goes to D, M to M, PC to PC, J to J, and SB to SB. The A star flag output of the control unit, I'm not really sure where that goes right now, so I am going to leave that disconnected and we will come back to it. Let me try to rearrange some of these components to, I guess, make it look a little cleaner. Not sure if that helps at all. Maybe a little bit. Now the register output should feed back into the control unit, and you can see starting with A here, it lines up perfectly. We have A all the way through PCB coming out of the output of the registers, and then A through PCB on the input of the control unit. So we'll grab these and maybe try to kind of pin them in a way that hopefully makes some sort of sense. But we are just lining everything up. D to D, DB to DB, M to M, MB to MB, PC to PC, and PCB to PCB. All right, that looks okay. And that completes our hookup for this registers component. So now let's finish hooking up the control unit, at least what we can. You can see that there's an I input in the control unit and an I output from memory. So we're gonna hook those up, maybe pin it around here so you can see better what's going on. And there's an A star input here, a 16-bit A star input. And you can see there's no 16-bit A star output for us to connect to this input. There's our star A output of the same control unit, but that's just 1 bit. The only thing left that makes sense is this X coming from the memory. We already have I coming from memory, so I'm guessing X and A star here line up with each other. It's a bit tough to remember what all of these flags and inputs and outputs do, so that's why I'm sort of guessing here at where they all hook up. So now we just have to deal with this memory input. This M input probably comes from the M registers. That makes sense to me. Same thing with PC. And A as well seems to make sense. The only X output that we can hook this input up to is coming from this control unit. So I'm just going to try hooking it up to this control unit. And that's almost everything hooked up. All we have is this ST flag in the memory and this A star output from the control unit. They're both 1 bit, so I'm guessing those line up with each other. Again, I don't quite remember the logic or the explanation of all these flags, but that seems to make sense to me. And that is everything hooked up. So unless I did something wrong, this is it. This is the last level. This is done. Just have to check solution, and then I'm done with the game. Let's try it out. There we go. 5 components used. And the level has been successfully completed. All levels in blank completed. Well, just all levels completed. We did it. We finished. I don't think there's anything after this. Let's hit next level and find out. Congratulations! You have completed the game. You now know more about how a computer works than most software development professionals. I loved it. It was great. I should probably email all the typos I found to this developer. Thank you so much for making this game and making it for free. Really appreciated. Really had a blast completing all these levels. It took quite a while, especially this last multitasking CPU section. But it was fun, and I hope this walkthrough helped anyone that's trying to solve these problems or just trying to understand how a computer works. If you've watched this whole thing, thank you so much. And this seems to be in active development, so if there's any updates, any new levels, I'll be sure to come back and add those in. And again, thanks for watching.